year, I think the dean said, Ettori hit the ground running. He's still running. So, any NSF grant, many students, excellent teacher, research with students, collaborations. As a formal education, Ettori did his undergraduate, master, and PhD at the University of Milan. He followed up with postdocs at the National Research Council in Trieste, University of Milan, and the College of William and Mary. And he started here in 2018. He's associate professor. Without further ado, let's
Thank you very much and good afternoon, everybody. Let me know if you cannot hear me or if I need to talk louder or anything. Okay, so what I wish to do with you today is to actually introduce one of the newest research fields that exist in physics, which is the field of ultracold atoms, which is a field which exploded in the mid-90s when the first Bose-Einstein condensation was realized experimentally. I have been a researcher in this field for now like 15-ish years. But I didn't want to do the talk about my research in the field, but about the field itself. Because it's a field that most people are not really aware of, despite the fact that American Physical Society created an entire division of DAMO in which this topic is growing stronger and stronger. But I thought it was interesting in a colloquium to really set the foundation for this, in a sense, sibling of condensed matter physics, much smaller field. And I will hope to be able to emphasize how the two fields connect, how they can help each other, mostly how atomic physics can help condensed matter physics, and how much fundamental physics sort of underlies the field. That's my main focus here. Now, before I move into that, I just want to acknowledge the very good list of students that I had the pleasure to interact with since 2018. And the group of collaborators that I keep interacting with. The most active collaboration as of now being people at UC Davis, Rice, Harvey Mudd, and New York. But those people have been like consistently interacting with me. And the main point of my personal, of the group's research is to do computational study of cold atoms. And all those are research results, which are here essentially as pictorial. I will not go, this will be a very high level talk. I want today to really dive into the foundations of the field. What I would like to mention is that since 2018, the group here has been very productive. We got 13 research papers in, one, hopefully plus one pedagogical, so hopefully 2 pedagogical papers. The American Journal of Physics has been the slowest journals I've ever had the pleasure to interact with. And to me, one of the most amazing things is like 32 presentations gave by students. We are funded by National Science Foundation, and I just wanted to showcase not all my papers in this period, but all the papers that included students. In particular, students as first authors and the students in top journals like Physical Review A and so on. Now, that being said, what's the point? If I had to summarize what this ultracold atoms business is to essentially create a quantum system in a lab. So essentially my talk will be over what is a quantum system, because you might feel, well, everything is a quantum system, isn't it? And that would be true. So we want to give clarity about that. And also why we want to simulate in the lab, considering that we have so many of them around us already. So why do we want to invest? And hopefully I will be able to convey some message there. But my starting point will be to discuss how do we distinguish a quantum system from a classical system. And so, I mean, the theorists in the group might tell you might tell me, no, you're wrong here, because everything is a quantum system, true. But there are systems for which it becomes essential to go beyond the Newton's laws and to use quantum mechanical equation, while many other systems, despite intrinsically quantum, can be understood to a huge accuracy just using classical physics. Also, the next question is, if we want to build quantum systems in a lab, what is our raw material? What do we choose? What do we pick? And in particular, why? And also, I will discuss with you how do we really set up the lab, how we create and control those systems. A very fascinating physics topic, which is cooling realized through light. And I would like to go, but most people are really not familiar with this, how we trap those systems so they are there in our lab. And perhaps arguably the strongest point about this possibility is that once we realize these systems in the lab, we can tune the forces. And that's something that in ordinary physics is unknown. Like, I cannot change the force between two electrons. Try, you will see you will not be able. I will not change the force between the Earth and the Sun. Those are written in the fundamental laws of the universe. But in these systems that I sort of artificially build in the lab, we can do that. Same particles, we can tune the experimental condition. The particle would go from attractive to repulsive to non-interacting to extremely strongly correlated, all in the same scenario. Finally, I will draw some conclusions. But let me start from the very beginning. What is classical and what is quantum? And the answer, everything is quantum, but many things can be studied with classical physics. That's an acceptable answer. But the parameter between the two is something that was written down something like 1 century ago, or a little bit less. I imagine most of you met this formula at some point. That whenever, and is a formula frequently mentioned in the discussion about waves and particles and duality and so on. Meaning that if you have a particle with linear momentum p, you can look at it as a wave with a wavelength that has that expression. This is due to de Broglie, a French scientist whose name tend to be destroyed when Americans try to pronounce it, even way worse than mine. So that's I think. Anyway, if you want to pronounce him correct, that would be de Broglie. Another very important thing that some of you from a physics 4B standpoint might have met before, and that is that the average kinetic energy is proportional to the temperature. Now I put the 3/2 to be precise for those of you. I don't want to mislead anybody. Normally in a talk you would never write that 3/2. But in general, that would be the correct form. Now, if you imagine to put those things together, extracting a typical momentum and plug it here, you discover a quantity that is very dear to statistical mechanics people. Some constants change a little bit, is not a strict equality. So pi comes out a little bit out of the blue here. But this quantity, Planck constant divided by the square root of mass times temperature, is a very relevant quantity that goes under the name of thermal wavelength. And you can look at it as the typical size of the particle as a quantum object. So imagine you're getting closer and closer and closer to that particle. At some point, you realize that that is not a point particle, but it has this wave structure. That is the length scale that tells you that. Now, the other crucial parameter we need to consider is how many particles, how dense is your system. Because how dense is your system tells you how close to each other the degrees the particles are. So the next step is, okay, we discover that we have this quantum size. And if you take the volume per particle and you extract like a cubic, like to the power 1/3, you get a typical distance between it. Now we know from StatMech that the system behaves in a strongly quantum mechanical way when the particles are close enough to recognize that the other guy is not a particle but a wave. And for this to happen, you need the density, you need this typical spacing to be of the order of this extension or smaller, right? So notice that if you have a light system or a cold system or a very dense system, all those are situations where this condition are met. Now, what about typical systems in nature? Well, let me start from the arguably the most common system, well, apart from dark matter discussion, but the most common system that we are aware of, electrons in metals, or even in general electrons in material. Now, for those systems, what you discover, plugging typical room temperature numbers, is that electrons tend to live a fraction of a nanometer from each other, and their thermal wavelength is around 4 nanometers. So this is definitely a quantum system. On the other hand, if you take a glass of water and look at the water molecules in the system, still at room temperature, well, here, actually the average distances does not change too much, but the thermal wavelength, essentially due to the much larger mass of the water molecule, becomes dramatically smaller. So essentially, the particles are sitting 1,000 times the thermal wavelength away from each other. So it's very hard for them to recognize if there is any difference between a particle and a wave. So you can water is actually very difficult to study, but it can be studied with classical physics. Another very common natural quantum system is the famous superfluid helium. Here you need to go very cold, around 2 Kelvin. And what you discover here is that the particles are still a fraction of a nanometer, but now the thermal wavelength is not that same order. So some systems are quantum and some systems are classical. But you might have a sense from a slide like this that quantum systems do not seem to be rare, like, because electrons in materials are ubiquitous. I mean, everywhere I look around, I will find this quantum system. So why do we want something else? Well, consider electrons in material. The first observation is that you have virtually no control on that system. It's an extremely complicated system. And you have impurities, you have the lattice, the interactions are very complicated to study. And I'm not meaning that it's not interesting. Actually, this is the essence of condensed matter physics. But it's a very complicated system to study. In theory, it's extremely complicated. Accessing observables that involve the electrons is very tricky. You normally need to go through some indirect probes involving conductivity, thermal properties, and so on. And those electrons are always stuck inside the material. So it's very hard to look at them. Now, on the other hand, if I could create the intention of cold atom experiments is to create something that is extremely clean, meaning that we can get rid of all disorder, we don't have impurities, we don't have phonons in the system, we don't have particular material-dependent properties. It's extremely tunable, controllable, and the latest frontier is that people are becoming able to observe those systems essentially at the level of a single particle in motion. No way to observe a single electron in motion in general. Although there is being tremendous progress also in condensed matter physics. Now, hopefully I gave you some sense that there may be some good interest in creating quantum systems using cold atoms. But the first question is which atoms? And essentially, people pick, well, historically they have been picked essentially from the first column of the periodic table. Nowadays, people are expanding to the second, where much more physics seems to be present. But just to give you a quick list, you will recognize the essentially lithium, sodium, rubidium, those are cesium, those are the big standard guys in cold atomic physics. More recently, people have been looking into like strontium, even ytterbium, which despite it lies somewhere else, it has an electronic configuration which is very similar. They now call it alkali earth-like. Although it's not obvious because it's down here. But if you look at the electronic configuration, it's pretty similar. Now, why those? Well, as usual in physics, one of the first parameters is simplicity. Those are the simplest atoms we know that we can use for this. Because the first column has only one outer electron. And usually that's the only electron that is really relevant for the behavior of the atom itself. Also, and this I will discuss in 5-10 minutes from now, those atoms are great in their ability to be cooled with light. I will discuss that in a moment. Most of them are very stable. The only really unstable one would be this guy, number 87, called francium. People try to use that, but that's pretty radioactive and not that abundant, so people normally ignore it. Also, they are very easy to collect as a gas, because the vapor pressure is such that if you put those in the oven, they evaporate very quickly and you can create a very nice beam out of them, while for other atoms it's definitely not. And also, due to that single outer electron or two, they have a very clean internal structure that is tunable with magnetic fields. That makes them pretty unique. Now, if some of you, and also using those, you can easily access both fermions and bosons, because those are composite particles. So depending on which isotopic species you use, you can have half integer spin or integer spin. So in the same lab, you can have a system that you can easily tune from Fermi to boson simply. Now, maybe some of you, mostly from StatMech, in particular if you attended my StatMech class, I might have tried to convince you that the simplest group in here is not this, but it's this. Well, that is a completely different story. Those are atoms that are very inert. Those are atoms that do not interact with anything. They are very happy to be standalone. For some StatMech models, they behave greatly. For this particular application, they are not that friendly. You cannot really cool them, and you definitely cannot tune their interaction as you can do with the alkaline elements. If some of you is listening very carefully, you might have noticed that in my list I didn't mention hydrogen. So that may be a complaint. Because you say, well, you told me choose the simplest and you don't pick the simplest. It's true. I'm guilty of that. The point is that, first of all, people tried that. And in 1998 at MIT, they did about the Einstein condensation of hydrogen. But apart from that, people in this field do not like hydrogen because it's very reactive, it's very active in a sense. It tends to stick to the surfaces pretty dramatically, so it doesn't really allow to create a very nice behaved, let me call it gentle quantum system. Now, so this is our playground. We basically pick atoms from, well, you can ignore ytterbium unless you want to become a specialist in material. Although nowadays it's becoming one of the most interesting for SUN symmetries. So even people from quantum field theory are looking into those quantum systems. But let me stay on the first couple. The one I'm mostly interested in personally is lithium, because it's the simplest fermion that lithium-6 is the simplest fermion that you can realize in this system. Potassium is also in that one. But now that we have a playground, how do we use them? Well, first of all, maybe you know, maybe you don't, but it's important to know that almost all of those at room temperature are just solids. The only one would be rubidium that can even be a high density liquid and close to room temperature. All the other ones are solid. And the first thing you would do is you just place them in an oven and you heat them up. What happens is that a lot of atoms escape from the solid phase. They form a gas with a given thermal velocity. And if you give them a path that acts also as a velocity selector, because I mean, like atoms travel everywhere here, but if you open only a narrow path, you just capture only the ones that are going in that direction. So easily, with an well, I'm a theorist, so I will never try that myself again. But it conceptually seems simple that if you heat them up, you can have this beam of particles running in that picture from left to right. And as you do that, those are in a gas phase, pretty warm. You get to between 100 and 700 Celsius. Essentially, you're dealing with an ideal gas. Because the typical dense, you find particles moving around a few hundred meters per second. And the density are around 10 to the power 12 per cubic meter. This is a very dilute system. So essentially, you have a very simple ballistic motion there. Now the next thing is, since we would like them quantum, something that we need to do is slow them down. Quantum mechanics tends to dominate at low temperature, where things are slow. So those are still too fast. This is essentially just a classical ideal gas. For that system, almost perfectly PV is equal to nRT. It's no more complicated than that. Now, this is the first interesting fundamental physics thing that I wanted to mention. Because we cool down these atoms with light. When I discovered this, I was pretty amazed, despite already having a PhD, because I had no clue that light can cool things down or slow things down. Because I mean, when I walk in the room, I don't feel a drag. Do you? Like, there is light here, but I can run in the room. If I run in the ocean, I feel a drag, right? But if I run in this room, it's not that if I switch off the light, then I go faster. Atoms do. In particular, if you design things properly. Because what people do, and it's very simple, is you take a laser light and you send it against the beam. So let's see what can happen there. And every time you have an interaction, it's like a small kickback. And if you keep doing them, the result is you have a gas of atoms that now are very slow. I will give you precise numbers. Essentially, what you realize in this chamber here is that of your family of atoms, they were going around 100 meters per second. You slow them down to something like 10 meters per second. So with your car, you can pass them. Just to have an idea. Because we are getting into slow stuff. And later on, I will discuss what happens when they enter this magneto-optical trap. Let's give me a moment for that. Now, how does it work? Well, imagine an atom that is going with velocity Vx along the axis x. This sounds like a 4A class. But at the same time, imagine a laser light tuned at frequency nu, going exactly along minus x. If this were my 4A class, I would ask, well, no, 4A is too early to know the velocity of laser. But in vacuum, the laser goes at velocity c, right? Very fast. The atom is like a turtle. The laser comes to him. But we keep sending the laser, right? So it's literally a beam of photons hitting the atom. Now, the interesting thing that comes from something that might be familiar to many of you, mostly from acoustic stuff, is that there is a Doppler shift. Meaning that if I am sitting on the atom, and I'm moving this way, and that is the photon coming to me, I see that at a different frequency. I mean, you mean, is that correction big? No, but enough. To the atomic precision, that is a ridiculous number. Like, the denominator is 300,000 kilometers per second, the numerator is 10 meters per second, so ridiculous, right? Everyone in a calculation pen and paper would neglect it. Not atomic physicists. Because in the realm of atom, transitions are so precise and narrow that is definitely a detectable matter. Okay? So So this is something that sort of a prerequisite to them. Now, another consideration to do. Say we are at 500 Kelvin in this region. Now if you move into EV, you are around 400 of EV. From the atomic physics point of view, this means that all those atoms are in their ground state. Okay? There is not enough thermal energy to populate any excitation of the atom, in particular of alkaline atoms. Now I remember the hydrogen numbers, not the other elements, but it takes much more energy than that, of the order of 10 eV, to excite hydrogen from the ground state to the first excited state. So imagine a bunch of atoms all in their ground state. So for lithium is my favorite, also the simplest I study. For lithium, you have 2 in the 1s and 1 in the 2s. If you're familiar, this is the spectroscopic notation. Now, the laser light that we choose will try to stimulate a transition like this. We'll try to create, and this is called the D2 line for lithium. The energy of it is around 1.8 eV. So notice much higher than the temperature. So the temperature cannot be doing this. Only the laser can do this. But the setting is like this. We do not tune the laser exactly at that frequency, but we tune it a little bit lower, so that when the atom is traveling toward the laser light, the Doppler shifted frequency matches the resonance. Now, that's interesting because, again, let me imagine Doug is my photon and I am the. If I'm moving toward him, I see exactly the resonance frequency, so I will get on my excited state. On the other hand, if I'm running away from him, I don't even see it. Because in atomic physics, you would see the photon only if the frequency is right. I will be entirely transparent to all other photons. That's a bit extreme as a sentence. So if I were in an atomic physics class, I shouldn't say it that way. But that's the concept. Actually, the resonance says that I will interact with the photon only if the photon has the exact energy that I need. Okay? And that's because at some point I'm moving in that direction, I basically absorb that photon. Then I would re-emit in a random direction. But the net result is that I get a bit of a slowing down. And then people keep tuning the laser or do something more complicated. But the result is that our atoms move slower and slower. Hopefully, now there are other things, there are Siemens lowering shear pain of frequency, but the main concept is this. We have this atom flying through this chamber. There is a laser light which goes against them, and they will be slowed down by it to the point where I have a bunch of atoms that are moving extremely slow, that are captured in this thing that is usually called magnetic optical trap. So imagine I am the atom. At the beginning I was in the oven, so I was able to run out of the solid phase. And then I found the hole, and I got in the chamber, and I received a bunch of photons that slowed me down, and then I remained trapped in this trap. Now the trap is a combination of two things. One are those kind of laser light which comes to me through the 3 orthogonal directions, from the front and from the back, coupled with, so the first thing is I have these 6 counter-propagating laser light, all being rather tuned, meaning they are all at a frequency which is slightly lower than my resonance, my transition frequency. But at the same time, the atoms in this region see a magnetic field gradient, which is also acting on the system. Now, this would be a talk on its own if I wanted to explain very carefully. But the point is, the internal levels of electrons in these atoms depend on the magnetic field. It's called the Zeeman effect. So if where I am, I experience a different magnetic field, my transition frequency can change. And if my transition frequency can change, also my interaction with the laser light can change. So if I engineer things correctly, I can set up the magnetic field so that the laser light keeps kicking atoms back, as if the atom were bound by a spring. So essentially, you create sort of an harmonic potential that confines the atom at the center of this magneto-optical trough. This is the physics involved. Now, if any of you is either passionate about ENM or teaching ENM, you just set up the problem of the anti-Helmholtz coils. I'm not sure you heard about the Helmholtz coil. The Helmholtz coil are just two parallel coils with current circulating in the same direction. That is one of the best ways to create a uniform magnetic field. But if you make them anti-Helmholtz, meaning you switch the direction of one of the two currents, that is one of the standard ways to control a gradient of the magnetic field, which is what is wanted here. The simplest version of it is that you can create a magnetic field whose Z component, for example, close to the origin is proportional to Z. This is not a difficult exercise, although it would require a class, not a colloquium, to go through the details of it. And in this way, we have our cold gas. Well, I hope this was sort of enough to give you the general sense. If you want a little bit of numbers, the temperatures that you reach at this level is of the order of a few millikelvins. Remember that we started around 500 Kelvin so it's a very significant cooling that can be achieved this way. The average velocities are around 1 meter per second. You can pass them walking. So those are atoms that move like this. Can you believe that? So if you imagine, you have an idea how fast are the air molecules around. Those are things that move like this. Well, they are quantum, so I cannot really, but I find it fascinating. Those are atoms that mostly crawl, don't even walk, okay? Now, there is a second layer of engineering wizardry which involves additional operation, where nowadays people achieve the spectacular temperatures. Can you imagine 1 billionth of a Kelvin? Now, this is more complicated to do, although the technique is almost the same. The last thing is something that they call evaporative cooling. So you imagine an harmonic potential where you gradually lower you sort of create a plateau which gets lower, 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 so the higher kinetic energy, they just fly away. And what you remain with are the cooled. That's essentially the same thing, like if you have a soup in your bowl, if you wait, the hotter, since the bowl is not a closed container, the hotter does go away, so if you wait, eventually, those will be gone, right? Now, just to make a summary, essentially, we have a system, and you can measure those things, that the typical distance between two of those is 0.2 micrometers. This may look tiny, but it's huge. But if you remember, electrons in the material are around 0.2 nanometers. So those are 1,000 times farther from each other, and they move like this. Right? The thermal wavelength is around 2 micrometers. Now, if you are interested, the typical traps themselves are of the order of 30 micrometers. So it's a little bit debatable if you could call those macroscopic quantum systems. Is that a macroscopic system? The number of atoms is around 10,000 to 100 million atoms, more or less. And their average separation is actually huge with respect to the range of the forces, right? Because the forces are electrostatic forces. Right? you take two lithium atoms 1,000 times farther away than the size of an atom, can you get a force? That's the next question. Because you might think, well, I have a great system, it's very dilute, but it might be useless because they are so far from each other that they don't even see each other. But not really. The huge achievement of this is that the atoms in this configuration will never solidify again. That's important because your point is to make a quantum gas. If it solidifies, and at that temperature you might be suspicious, will it stay a gas at that temperature? 1/1000th of a Kelvin. Have you ever seen a gas at 1 billion? But those do, because they are so far from each other that crystallization cannot take place. So that's something important. But the other big point was that, how about the forces? Because we know that atoms are very far apart. Now, the range of the actual atomic forces is a few nanometers. So most of the time, those particles will be just in freedom, right? Also, the thermal energy is ridiculous. Like, we are at 1 billionth of a Kelvin. So essentially, there is no way there is enough energy to generate angular momentum. Right? So essentially, all the collisions will be just straight like this. In the language of quantum physics, this is called an S-wave scattering. And you say, well, those systems may be nice to make, it can be a nice game, but are they also useful? This can be an image of what you will see in a lab. Now, the point is that in the region where you have these atoms, you can switch on, you can have a magnetic field, you just need to bring the coil. Right? And the key point is that by tuning this magnetic field, you can dramatically control and affect the interatomic forces. So the next question for my next 15, 20 minutes is, how is that possible? Because we have those things so far from each other. And you say, are you telling me that just switching on a magnetic field and adjusting it, can you make the interaction you want? Doubt it, right? Imagine there is me here and Doug may go to Los Angeles and I say, well, I tune the magnetic field and I suddenly attract him so that in a few seconds we are splashed in the park. Well, you say, well, you probably watch too much TV. Anyway, how is that possible? And here I'm talking about lithium. So to have a quick look at this, I need to remind you something of very basic two-particle scattering from the quantum mechanical point of view. Now, this might remind you a lot about the hydrogen atom. Imagine we are talking about the relative coordinate and we are looking at two atoms moving around each other. Now, when we think of scattering state, we consider positive energy. The rest is identical to the hydrogen atom, so you can look for, some of you might know that under the name of separation of variables. However you got to this, you might have seen something like this before. And also, the thermal energy is so low here that we don't really care about the angular momentum. We take L equals 0, so everything becomes just a trivial radial problem. And trivial radial problem basically means that we need to solve something like this. We have an interaction, we have so on the radial side, no angular momentum, so no centrifugal barrier. Everything very simple. And also we know that when particles are far from each other, essentially this, which would be the interatomic potential, will certainly be negligible. So the only thing we would have is something like a free particle solution. Now the only signature, the only fingerprint of the potential of the interaction would be something which is just a shift. It's a very famous in scattering theory. Imagine this would be the interaction region. So here we would be very far away. And the only difference between the non-interacting physics and interacting physics would simply be a change in the phase. That's an important point. In 5 minutes you will understand why I'm telling you all this. So, this, apart from some amplitude, the key point will be this shift. And the interesting thing is that if you have this information, you can write down arbitrary scattering states. You can actually set up a basis of scattering states. And this gets this pretty interesting form, where you can write your solution for a two-body quantum physics as a plane wave, which you interpret as an incoming part. And then you have a scattered spherical wave, which has an amplitude which critically depends on this phase shift, right? And when you are at very low energy, you don't really care about the full delta zero, you just care about the zero momentum limit of it. That defines something that we call scattering length. And all this complicated term becomes a pretty simple thing, where all the effects of the interaction which were here are just encapsulated in a simple quantity, which is the dimension of a length. That's a very important thing. Because essentially the scattering states at very low momentum become something like this. So you notice that how far away the particles can be when you still feel the interaction critically depends on this A0, right? So if you bring R as big as A0, you still feel the interaction. That's what a formula like that. Even if the actual range is tiny, but if that A0 happens to be big, then you do feel the effect of interaction even far away. Now, can that A0 be big? Well, you can do a very simple exercise. You set up, this is probably the simplest potential that you could imagine, apart from non-interaction, right? And you can make the analytic calculation of what is that scattering length. And you can plot it as a function of the depth of the well and the range. What you find is something very peculiar. Now, if the well is repulsive, meaning that it's U0 in this notation is negative, then the scattering length is a pretty boring function. It's positive, it never gets that big. It always remains of the order of the range of the interatomic potential. But if you solve the problem for an attractive potential, it looks very, very nervous, right? So if you change either the depth or the range, you go from negative to positive passing through divergences. Those divergences are called resonances. Physicists all tend very commonly to call divergences resonances, but that's a different story. So what's the point of all this? Well, if you think of what I told you before, that essentially it's only a matter of phase shift, what happens when you have these explosions is that the phase shift basically becomes 90 degrees. So the non-interacting would be mostly like this, while the interacting would be entirely. But you might think, well, is it any different? Because it looks like more or less a constant, right? Well, it is very different. First of all, because imagine this number explodes. Now this amplitude of the scattering wave function would diverge at zero momentum, meaning that your scattered wave has a diverging amplitude. So infinite scattering length means extremely important interaction. That's not a super precise term, but does it convey it? It means that interactions are indeed very strong, even though the actual force has a tiny range. And U0 doesn't need to be huge. I don't need super strong forces to create super strong scattering events, scattering amplitudes. Okay. And if any of you is willing to teach or learn those through basic quantum mechanics, a very fascinating thing is that those divergences co-arise and are directly related with new bound states arising in the well. So you can count, depending on the depth of the well, how many bound states exist in the well. As every time there is a new one, the scattering length explodes. That's an interesting, it's not a coincidence, but it's an interesting co-arising. And another fascinating point is that if instead of simple plane waves, you consider wave packets, so something that physically changes as a function of time, what you discover is that when you are near a resonance and you compare, say at the same time instant, a scattered wave packet with a situation which is off resonance, the one near the resonance remains backlogged. Means there is a delay. This means that the particles spend more and more time close to each other, because before you see the scattered wave packet, you are backlogged. And this backlog can diverge on its own. So essentially the two particles meet and stay together. That's another sign that those particles can interact very strongly. So hopefully this conveys a sense that despite in lithium, in those gases we have particles that on average are extremely far from each other, but if it happened that the scattering lengths were big or diverging, then that wouldn't be an issue, because we would still have a system that interacts very strong. But you might still be suspicious and tell me, well, okay, but how do I know that the scattering length? Because, I mean, the forces are what they are, aren't they? So the scattering length might be just a tiny number, so my effort is gone. Now, the issue, and that's the great thing about flashback resonances, is that if you switch on a magnetic field, you can move that scattering length. How so? Well, this would be a pretty big discussion, and this is exactly the American Journal of Physics that I'm hoping that it goes through pretty soon. The key point is that a lithium atom is not a point cloud. What I mean is that there are some internal levels. And now lithium is also pretty, like, let me put it like this. There are so few electrons that they remain so close to the nucleus that they see the spin of the nucleus. That is something that in atomic physics is often skipped. It's called the hyperfine structure. Because when you're very far from the nucleus, you're far enough that you don't really see that. But lithium, they do see. Hydrogen also. And all of those. So essentially, something that sounds extremely simple, like 1s2, so 2 electrons in the first shell, and then 1. If you look more carefully, that corresponds to 6 levels. Those are hyperfine levels. And if you think of it, combining the magnetic moment of the electron with the magnetic moment of the nucleus, you find another magnetic. So if you switch on the magnetic field, you have a problem of a magnetic moment in a magnetic field. And that's tunable, because the energy of that, the magnetic moment will try to align to the field. And so depending on where is it pointing, it will have a different energy. It's as simple as that. It's called Zeeman effect. So you can model this as a system with 6 internal states. Now, if you have more than one internal states and you still look at the collision, you not only have an interaction term, but you also need to take care of the internal Hamiltonian. That's another still pretty toy, but it's the next level approximation of the problem of 2 lithium atoms. Incidentally, you might think, well, 2 lithium atoms, I might be able to get the exact solution. Well, careful with that. Because you have 6 electrons, 2 nuclei, you will need relativistic correction. So if you try to attack it brute force, good luck to you. Pretty long endeavor. But the simplest level is we consider, well, there will be a kinetic energy for relative motion. And the relative motion is certainly non-relativistic because we have things around 1 meter per second. So relativity there is not extremely important. It's like moving a turtle with Lorentz transformation. But that doesn't apply to the electrons in the atom. That's a different story. So when the simplest way to see that, to look at the internal, is just consider those 6 states. And then you will have an interaction term. And you need to remember that if those are lithium-6 atoms, those are Fermis. So you need an antisymmetric coefficient. So in general, you will have states that have a radial part, but they will also have an antisymmetric combination of internal states. Now, the technical term for each pair of states is a channel. So this is called a multi-channel scattering problem, because the particle can come to each other in different internal states. And that creates that effect. And the sister of the radial equation in a multi-channel environment is a little bit more complicated. Although not that much. Because you would have, this is what this and this were already there. You will need the internal energies, and I emphasize that are tunable with the magnetic field P. And now you need to consider that there is no reason for you to assume that the interatomic forces are not able to induce transition among those levels. So in general, I need to consider the possibility that that is non-diagonal in that basis, meaning that if they come in given hyperfine states, I don't know if they will remain in those hyperfine states, because the interaction energy can have them jump to a different internal state. So that's why the left-hand side is a little bit more complicated. All those different from are due to Fermi statistics. You cannot have the two in the same. So the overall wave function wouldn't be anti-symmetric. But the beauty of this problem is that it's tunable with the magnetic field. Essentially because those levels are tunable, so the problem itself is like you have an additional knob that you keep changing and the parameters of your equation keep changing. But experimentally. In theory we can always change the parameters, but whether nature will change the parameters, that's a different story. Now, this was what I started from. If you want to make it for particles with internal